Okay, we're live. A very good evening to everybody. Welcome to day one of NeuRes, a week-long series of webinars hosted and conducted by the data science community of SRM. Today we have speakers Shinjini Mehti and Arsh Chaube, who will be discussing the intuition behind the basics of deep learning. We hope you will find this webinar very fruitful. At the end of the session, we will be conducting a short quiz for all of you, on the basis of which the winners of the prizes and the swags will be decided. And the link for that quiz will be shared on the #NeuRes channel of the Outer Circle Discord server. I'll just repeat that. The link for the form will be shared on the Outer Circle Discord server for the quiz. So at the end of the session, now I'd like to invite the speaker so that they can present their screen and begin the session. Guys, go ahead.
So, hello everybody. Welcome to this session on Introduction to Deep Learning. It's great to be speaking with you all today. I am Arsh, and I'll be presenting the session along with Shinjini, a fellow member here at DSC. So, let's have a brief account on today's topics. So, we'll be going through what is deep learning, neural networks, perceptron model, activation functions, cost functions, optimization, gradient descent, and in the end, we've prepared a small notebook for you covering some of the concepts which we thought would be great to implement using NumPy. And of course, you can dabble with it in your own free time. We'll be giving you the access to that as well. Without further ado, let's get into it. So before I get to what deep learning actually means, I'd like to know if you all are familiar with machine learning, the machine learning workflow, or anything related to machine learning. So I'll quickly create a poll for you guys, and you can just say yes or no for that. Yeah, so I've started the poll. We'll wait 10 to 15 seconds for this. Yeah, okay, so I see majority of you guys are actually familiar with machine learning. However, for those who aren't familiar, I'll just give a really brief intro to what that means and what that is actually. So machine learning is just an application of AI that provides a system to ability to learn from data. So now there are various types of machine learning. There could be there's unsupervised learning, there's semi-supervised learning, there's supervised learning, there's reinforcement learning, etc., so on and so forth. Currently, we'll be focusing on supervised learning. So what supervised learning means is that, let's say you have a given input data X and you have an output variable Y. So you choose an algorithm to learn that mapping function Y is equal to f of X. Now, many of you in your high school times would have seen the line Y is equal to mx plus c. So this is exactly the same equation I'm talking about. Now, the goal of that is to approximate that mapping function so well that when we have a new input data X, we can predict the output variable Y for that data. Now, there are generally two types of tasks in machine learning. One is regression, supervised machine learning I'm talking about. So one is regression, and the other one is classification. So regression, put in simple word, means prediction of continuous values such as price, salary, age, etc. And classification is used to predict or classify discrete values such as true or false, spam or no spam, male or female, dog or cat, and so on and so forth. Now that we are all set with the basic definition, I think that we are set with the basic definition. Let's see at how the whole process or how this machine learning thing or the workflow is going on. What is it about? So the first step, the first and the primary most step is to collect the data, because if you don't have any data, you can't do any operations on it. You can't learn. So you need to collect the data that your algorithm will learn from. Next step is data preparation. This is actually one of the most important parts in the whole machine learning workflow. So Data is usually, yeah, when you go out in the real world and try to gather data, it is usually in a really unstructured format. Like you guys would have seen, if you would have seen some Excel sheets, there are tabular columns and all the values are sorted along and segmented based on the categories. Okay. So, but in the real life, the data isn't actually like this. So we have data engineers for that. So they collect the data, they do the structuring, and then comes the next step, which is exploratory data analysis. So data is just a bunch of numbers, right? So you can't have any valuable insights from data. So to get the valuable insights from data, you perform exploratory data analysis. Now I won't get into the details of that, but you what you basically do is you look at the distribution of data, you look at if there are any missing values, you look at the correlations, and etc. The most important part here is extracting the important features. Now, features is a word I want you to pay close attention to, as this has a great significance when it comes to machine learning as well as deep learning. The next part of the process is training, also known as the fitting stage. This is where the machine learning algorithm actually learns by showing it the data that has been collected and prepared by the data engineer. The next part is evaluation. Obviously, you have a model, you've trained your model. Now you need to test your model and see how well it performs. And the last part, which is also an important part of the whole workflow, is tuning the model. Tuning the model, or optimize, as I'd say, because optimization is something we'd look in a greater detail later on in this session. So I guess that's about it for the intro for machine learning. I see I've digressed a bit. Nevertheless, let's get back on track. So what is deep learning? You must have seen everybody's talking about it. It's sort of a buzzword, and it seems like people have forgotten machine learning completely. And of course, that I mean in a really sarcastic way. So deep learning has actually revolutionized many fields, from autonomous vehicles to medical imaging to energy sector, recognizing speech, translating languages, and everything in between. And some of these tasks which will actually be performed later on in this webinar series, so be sure to attend those lectures as well. Now comes the question. I've already told you about machine learning, and since machine learning is able to learn from data, why do we need deep learning at all? So why is, I think, is one of the most important questions. So at this moment, I'd like to highlight a very crucial part of the machine learning workflow. This is called the feature engineering process. And like I said before, pay close attention to the word feature. Now, this topic, feature engineering, it's a whole new chapter to start on. But I'll give a brief intro to what this exactly means. So essentially, feature engineering is a process of using domain knowledge to extract features from raw data. And don't worry, I'll just break this sentence down. So let's see, given an analogy, let's say you are a sales manager for some company manufacturing some product. And you've been given a task by your CEO to predict the sales for the next 3 months or 5 months, maybe, and given some data. Now you have a look at the data, and it's a task heavy job. So you perform the job for the data engineer as well. So you get your data sorted. And now you see that when you actually look at your data, you see you have some columns. Now these columns could be the labels or the independent data, which will be contributing to your sales because you're predicting the sales. Now, for example, this could be the competition distance, competition open since months, store type, inventory available. And again, you'll perform some exploratory data analysis to actually see if any of these columns actually contribute to our sales. So this is basically known as the feature engineering process to find out what is actually contributing to our final output. So feature engineering, this can also be considered as applied machine learning itself. Now this process is a really tedious process. It sometimes takes months to get valuable insights from data. It isn't as easy as it seemed right now, because it isn't. But when you go out in the real world, sometimes this data is so dense that you cannot find any value or any variable that would be contributing to the output variable. So this is where deep learning comes to rescue. it really shines when it comes to complex problems such as image classification, natural language processing, speech recognition. Some of these tasks I already mentioned before. So deep learning has what it does is that it uses a artificial neural network as it's written over here. So you just pass over the data and it'll find out the important features for you, and this will save you from the work of manually handcrafted features. Deep learning has also been really important to handle data at large scale, because there's terabytes or petabytes of data, and this is where deep learning comes to play. Plus being and deep learning can also cover a wide variety of data, complex problems across different industries, like from autonomous vehicles to energy sector and everything in between. I'll just keep on repeating that because I think that's amazing. So, having said that, there's a caveat here. Don't think deep learning has replaced machine learning completely. There are many instances where machine learning algorithms still outperform deep learning, and you can have a look at it in your own free time. So, in terms of deep learning, at the heart, it's all about our neural network. So, what on earth is a neural network? Shinji, next slide, please. Right. So, an inspiration which is drawn from the human brain, note that it doesn't completely replicate the human brain. And we are nowhere near to how a human brain works. So, let's see how this neural network works. This looks like a really complicated structure for some of you who are seeing it for the very first time. So, let's start with an analogy here. So there are starting points X, let's say starting points in red. Let's say this is the input layer. And these are the ending points in blue, which we'll say are the output layer. Let's say these are islands somewhere in the Pacific Ocean. And we are traveling from the input layer islands to the output layer islands. Now, we can take various ways, as you can see, the hidden layers. There are tons of ways we can take from going to the to go from the start to the end, and each route has different points. So when we approach the destination, which is the output layer, we'll sum up all the possible scores and determine which is the best island given the four here in blue, which we are looking out for. So it's like sending our detection board teams to find out the perfect islands for the next vacation. One interesting part here is that when the board teams approach the output layer, which is the one in blue, they come back to the input layer. And then we repeat the whole process of sending them towards the output layer and calling them back to the input layer. And finding out the best possible route and best possible route to the best possible destination we want to arrive. So this was an intuition behind neural networks. The mathematical explanation to neural networks and the aggressive formulas will be covered in tomorrow's session. So be sure to join that as well. That's it for me now. Over to you, Shinji.
Yeah. So hello everyone. We are going to begin with the perceptron model, which is the most basic unit of a neural network. Now, why perceptron model? It is basically out of use and mostly used to explain neural network to beginners. We will begin with looking at the parts of the perceptron model. To the left, we can see there are the circles which are labeled from x1 to xn. We call those our n inputs. To the right of them, we have the weights, one weight for each input. We multiply each of the inputs with the corresponding weights and we compute their sum, which is called the weighted sum. The last step is to squash them into a value between 0 and 1. Now, what's the purpose of squashing it between 0 and 1? This one is used to compute for binary classification, which is to categorize an input into one of two classes. So it's really convenient if it's either 0 or 1. One thing I looked over is the W0. We referred to that as the bias. It is something that basically helps us to shift the value that we get to the right or the left of the number line. Now, we have understood the basic structure of a single-layered perceptron. Single layer because It is composed of just one layer, which is the input layer. There's something else called the multi-layered perceptron, which is basically the neural network that we saw in the previous slide. So I'll just go back for a second. So here in the neural network, we can see it's a bigger version of the single-layer perceptron model. The input layer is familiar to us, which is composed of red circles. The yellow ones are called the hidden layers because it's neither the input nor the output. Between each consecutive layer, we have a connection. The connection is associated with a weight so that when the input, the value flows from one neuron to this other neuron in the next layer, we multiply that value with the weight that is associated with that connection. Now, this was all about the neural network that we need to know. The basic unit is called a neuron, and a neuron is composed of two parts, which is a linear part and activation function. This activation function is what we will get to now. So what is an activation function? As I said, a neuron is composed of two parts, a linear part and an activation function. The linear part is what you can see on the screen. It is the input that we get multiplied by the corresponding weights, which I talked about, added with a bias. This value is passed to an activation function. Now, here we may have the question that why do we need activation functions at all? That is a bit of a different area that we will cover on tomorrow's session. We need to know some more about neural networks to know that. So after knowing where the activation function sits in a neural network, we can move on to the types of functions. So we have the formulas of four most common types of activation functions. The first one is the sigmoid. The sigmoid ranges from 0 to 1, and which is again used for binary classification, since it's very convenient, 0 and 1. Tan H. Tan H is visually similar to sigmoid, and it ranges from -1 to +1. And what's the purpose of squashing the values between -1 and +1? It helps us to keep the values that we use for computation manageable. We will look at the graphs for these functions in the notebook in a little while. Before that, we'll see ReLU. It's the short form for the rectified linear unit, and it takes quite obviously the maximum of 0 and x. Now softmax. Before moving to softmax, sigmoid was something we used to classify the input into one of two classes. Softmax is a generalized form of that. It is used to classify into one of n classes. So what does softmax do? If we have n neurons in the output layer, softmax gives us a probability score for each of the output neuron. It indicates that which class of the n classes our input belongs to. So after this, we will move on to the notebook for a second just to see the graphs, the plots. So this is the sigmoid function. As I mentioned before, from 0 till 1, used for binary classification. Now, the value, the output we get after using sigmoid activation function can be anything between 0 and 1. We usually set a threshold at 0.5, which indicates that if the value is over 0.5, it's 1, that the input belongs to the 1 class, and otherwise it belongs to 0. For tan H, visually similar, ranges from -1 to +1. The purpose of using this is mostly to squash the values, as I said, into a manageable range so that the computation doesn't get too heavy. For example, if the values are too high or too low in the negative side, it may get quite computationally heavy. The next is ReLU. Now, before moving on, I need to mention a problem we have with tan H and sigmoid. Quite apparently, if we move too high or too low, the slope of the graph is almost zero, it's close to zero. Now, a slope is something that we need to train our neural network. And if it's close to zero, it doesn't help us at all. So to solve that problem, we use this ReLU activation function. The significance of the slope is something that we will cover a little later in this session only. So the ReLU, quite evidently, it takes the maximum of 0 and x. So it's 0 when the values are negative, and the identity function otherwise. There are a ton of activation functions available, and this is a list of all of them. We are not covering all of them, but we have attached a link here for more information, and it would be really helpful for you guys if you just take a look at it. So after this, we will move on to something called the cost function. Once we know activation functions, we know that what are the parts that a neural network is made of. Now we can move on to the training. Now, between all of this, we should not forget that why at all we are using a neural network, why we are taking the effort to learn this at all. We are learning this so that we can predict some output for a given data. We need to get accurate predictions for data that we cannot do ourselves, or it's too tedious for humans. Now, obviously, the neural network cannot give its predictions from
Yeah, sorry for that, guys. Shinjini is probably having some net issues. She'll be connecting. Now that we've covered a lot of information, I don't see a lot of questions here. Guys, please keep posting your questions on the question tab, and we are happy to answer. If you have any questions about why deep learning over machine learning, or where does machine learning fail, or any question about activation functions or neural networks, can we get the link to? Yup, you will be getting the access to the collab notebook after I'm done with the session. I guess Shinjini is back.
Yeah, am I audible?
Yeah,
Hello?
we can hear you loud and clear.
Yeah, great. So yeah, so where were we? We were at the neural networks.
Shinjini, just a second. I
Yep.
guess your screen isn't visible right now. We'll wait for 2 to 3 seconds. Yeah, by the way, the analogy I used, the sales manager, it was actually my first project here at DSE. So I saw someone asking how can you join the community. So we keep having recruitments, and the moment you're selected, you'll have your project. And then you can talk about it like me here in some session. So that's about it. Shinjini, just try to present it once again, I think. So what are the prerequisites for starting with deep learning? So yeah, get your ML concepts really, have a solid. and start off with the theoretical and math part. And your high school math should be great. I guess Shinjini is back, so we'll get.
Yeah, we are back. Great. Okay, so we were at cost functions. That is what the neural network does. It looks at the data set, that is, it passes its input through the neural network and produces some output. This results in some output produced by the neural network. So we compare the provided output with the output that the neural network produces. And depending on how wrong the neural network is, we impose a cost on it, which is basically telling us how wrong it is. So the cost is something that is obviously imposed by a cost function. So higher the cost, we will have higher cost means that the neural network is more like worse, performing worse. And hence our aim is to minimize the cost, which signifies a low error. Now, before moving on to the mathematical part of a cost function, we will take a look at the graph. In the graph, the vertical axis is the cost function, and the horizontal axis contain the parameters. The ones that we see labeled as theta, those are basically W, which is the weights. Now, most of the times, in fact, almost all the time, it's not just two weights that we work with. It is quite a lot high number of weights, and we definitely cannot visualize that beyond this. So we settle for two. Here, it looks like a hilly landscape if we look at it just without knowing anything. And the hilltops here denote high cost, and the lower parts, that is the valleys, it means low cost. So we would definitely want to travel from the hilltops to the valleys, the lowest valley, as low as possible. Now, how do we do that is something that we are going to cover after covering the mathematical part of the cost functions. So yeah, this is the most common cost function, most used for regression, which is where we predict a continuous value, like predicting stock market, which is a value, stock market costs, or anything like house prices, which is the most basic task that people take over when starting with deep learning. Okay. So here we have to consider that there are n output neurons in the output layer, and I denotes the ith neuron in the output layer. Yi is the given output into the data set. Yi hat is the output that is produced by the neuron, that is the network. We take the difference and find the square, and that is denoted as the error. Now, obviously, people would ask why we square it. We square it because if we find some negative error and some positive error and we add them up, it cancels each other out and we end up with a low error, which is misleading. So here, which is called the mean squared error or the quadratic loss, here we add up the errors from the n output neurons. Hence, the I runs from 1 to n, and we then average over that. Now, there are quite a few other types of cost functions, but we'll cover only two more here. Before looking at it, we must, as Arsh had covered before, the difference between classification and regression. Regression is when we want a continuous value. Classification is when we want to classify something into one of n classes, that's categories. The previous one, quadratic loss, we saw is used for regression. This one, the binary cross entropy loss and the cross entropy loss, they are used for classification. Now we need to get into some math to understand the formula. Here, just like before, y is the provided output, y hat is the produced output. If y the provided output is 1. Here, the second term becomes 0, and we are essentially left with minus log of y hat. So if y hat is leaning towards 1, then log of y hat will obviously be high, and when we negate it, as is the minus in front of it, we get a low cost, just what we want because our given output is 1. Now if y hat is close to 0, log of it will be low, and when we negate it, it will become high, which we want because 0 is not the class we want. Now it is similar for when y is 0, and you can work it out yourself. I think you'll get it. If we move to the second one, which is a cross entropy loss, it says it's used with softmax activation. Now softmax activation, as said before, is used to classify something into one of n classes. Hence, it's just a generalized form of the binary cross entropy loss. We take the log loss, as it's called, of each output neuron, and we add over them. Okay, and there's another thing we need to cover, which is why don't we use the quadratic loss, which is this one, for classification as well? Well, that is because if we look graphically, using MSE for classification gives us a cost function that is too hilly, as we saw before. It makes it difficult to find the lowest point in the hills, that is the lowest valley. Apart from that, in that MSE is specifically made for regression problems. Hence, it becomes a bit difficult to handle precise values ranging from 0 to 1 using this MSE loss. Hence, this is what we use for classification problems. Now, I talked about that hilly graph thing that we need to reach from the hilltops to the lowest valley. That is something that will be covered by Arsh from now on. Before that, we'll have a small 5-minute break. You can head over to our Data Science Community Outer Circle Discord to interact with our members and get some coffee, of course.
So welcome back, guys. Let's continue where we left off. Okay, so the concept of optimization. Now, if you're in this guy's place right here, then you attended the right session. I'll answer all of these questions sequentially. So the first question that came into my mind when I was learning deep learning is what the hell is optimization? So in while giving the intro to machine learning, also at the last step of the workflow, I talked about fine tuning your model or tuning your model, and this is where the optimization part is. So optimization method is nothing but finding the optimal or near term optimal solution to our cost function with the lowest computational effort. That is what it is at the heart of optimization. Why optimization? So optimizers, what they do is that they help in reducing the error of our loss function and to get a better minimum. So I'll come to that later. If it sounds a bit intricate, don't worry. And where do we perform optimization? So of course, when we are training the model in the workflows, I guess training step, this is where we do the optimization part. When you have the data collected, when you've decided your model, and when you're about to train your model. After that, you do the optimization process. Who is the silliest question? Of course, you are the one who's doing it. And how? This is the biggest question, how. So one of the main optimization algorithms I'd like to cover in this session is gradient descent, which I'll be talking about in next slide. Gradient descent is an optimization algorithm, and some of the other optimizers I'll be covering today is stochastic gradient descent and mini batch gradient descent. So let's come to gradient descent. And of course, my life isn't as sad as this guy here, because look at the attendees. I have some vigor in explaining whatever I'm doing right now. So let's come to it. As Shinjini was talking about the lost landscape earlier in her slide, I'd like to recap it for you guys, because if in the break you forgot or something. So a lost landscape is just a visual representation of values a cost function can take, given on a given range of parameter values given our training data. So this might be our weights for the model, and this is where we need to navigate. The now comes the intuition behind gradient descent and what this is. So while preparing this slide, me and my fellow teammate here at DSC, we came up with an analogy. Abhishek, so he's a technical director here at DSC. So let's say Abhishek, whose life isn't as sad as mine, plans to go on a hiking trip someday, hiking tour maybe someday, and and all he can do is mathematical operations, and he's sort of dumb. So don't worry, he won't be offended for that. So what he does is that he plans to go hiking somewhere in Delhi. Now, as he can't find any place, he plans to go to the Ghazipur landfill in Delhi. So he gets up top somehow, and here this is the part where he gets lost. So he doesn't know how to come down, and obviously and go to his home and do his regular stuff of deep learning and all. This was the analogy part. Let's come to the math of the analogy part. Now let's say Abhishek is here at a starting point W0, which will be our starting weight, and the slope of this landscape, this represents our cost function, which I talked about in this slide. Okay, so this is the slope of the loss function, and the ditch here, we can say this is the minimum of our loss function, and this is where Abhishek is planning to go. Now, how does he achieve this task, since there's almost zero visibility and he is not logical at all? So what Abhishek does is that at each time step, at each step, he calculates something known as the gradient. Now you might be asking yourself that what is a gradient? So gradient is nothing but a direction. So he calculates the gradient at this step with respect to the. So this is, he's on the cost function landscape. So he calculates the derivative of the cost function with respect to the position he's at, and he gets the gradient for that. The next step he does is that he starts on moving in the opposite direction to that gradient. So let's say if he calculates the gradient like this, and this is the direction, he starts moving towards this side, and he plans to aim the ditch. Now there's one more. There's a big factor influencing his steps, right? The stride. How big a stride should he take? Now, since Abhishek is dash, fill in the blanks, you know that. He could be jumping here in the landscape and missing the ditch and going haywire. He's already lost up top, and he could be moving really slow like a snail, and we don't want that as well. We want an optimal step. He wants an optimal step he needs to take, because he needs to go back home and have his food at night. So in simple gradient descent jargon, in deep learning terminology, this is something we call as the learning rate. So the parameter alpha, the learning rate here, is a whole different story to talk about, and we'll keep that for tomorrow. I'll come to this tomorrow. As of now, all you need to keep in mind is that if Abhishek chooses alpha to be too small, he'll take too much time to reach down to the ditch. And if he chooses alpha to be too large, then he'll be jumping on the landscape and getting lost again and again. So this is the formula for that. This is your, now coming on to the mathematical parts. This is your weight, and this is how you update your weight. And this is nothing but the gradient you calculate for the weight. And this part here is the gradient vector, which I'll be coming on to in the hands-on session. So that's all about, so that's all about the theoretical part of this session. Let's move on to the hands-on session. Just a second, guys. So here what we have is that so what we plan to do here is that we'll implement a simple linear classifier and try to train it using stochastic gradient descent. And this is something which I haven't touched upon as of yet, but I'll be doing so as I move forward with the notebook. And we'll be doing this with the help of NumPy. So let's take a two-dimensional classification problem. To make things more intuitive, I already had some synthetic data with me. And this is how the data looks like. So I need to classify these data points. So as you can see, the reds and the blues. Now you can see that this data isn't linearly separable. That means I cannot draw a line and divide the data between the red and the blue. The only decision boundary I see here is some sort of a circle. And I think you might relate to this as well. And since we'll be using a linear model for prediction, which is the logistic regression model, I'll be coming to that. We'll need to add features, because we aren't using a nonlinear model here. We need to add quadratic features so that we can, cut this, or maybe form a circle, or, make this problem linearly separable. So this is the function here. So what we're doing is that we have the data, which isn't linearly separable. So the data is 826 rows by 2 columns. And those 2 columns, like I told you about before, those are the features which the data engineer manually handcrafts, right? So this function here, expandx, takes the input data and performs some nonlinear separation. Now this is arbitrary. And like I said before, you can dabble with it in your own free time. The first 2 rows I've kept as they were. And the rest of the rows, so I'm taking here, the columns. So I'm taking here the columns. So I'll be dividing this into 6 columns, and you can divide this into 7, 8, 9 as per your use case. Third column I'm taking as the feature 0 square. You can take this as cubed. You can take this as cubed. This part is here where you can have feature 1, feature 0, feature 1. This could be feature 0 again. And this is where I'm performing this operation. This is the code for that. Now this could also be done using NumPy slicing and indexing methods. The time when I was doing this, I was really new to Python, so I did it in a really raw format. Now when we pass our training data to this expand function, so this is what the output looks like. Now we have the training data with 6 columns, and the given rows, I think 826 are the number of rows. Next comes, so we've prepared the data here. Next comes the model. We need to choose a model. So we'll be using logistic regression. Now for those of you who don't know what logistic regression is a simple statistical model that in the basic form uses the logistic function, which is also known as the sigmoid function, which I think Shinjini had explained earlier in her slide, to model a binary dependent variable, although many more complex extension also exist, like multi-class logistic regression, and all of those things also exist. So here you have a sigmoid function, which so you pass in your data and the weights to this sigmoid function, and this will give you a range of values between 0 and 1, right? But what this is that we interpret these as probability scores. Now if I pass in my data, and as you can see the probability is 0.73. Now what does this probability mean? I mean, this means this could mean nothing to me, right, as my labels are 0 and 1 only. So I'd have to map this to a decision or threshold function, which Shinjini talked about in her slide when she talked about the sigmoid function. So we usually take 0.5. And then again, there's a caveat, 0.5. I'm not saying that it's a generalized value you need to take. It depends on your problem. But usually we take that if your probability score, in this case, it's 0.73. If it's above 0.5, then you'll classify that particular data point to the class 1. And if it lies below, then you'll classify that particular data point to the class 0. So now coming on to the probability function, it takes in the training data X and the W. Also, one major thing I'd like to highlight for those of you who don't know what machine learning and deep learning is, when we come to the computational part of this, the solving, it's just matrices and vector operations. As you can see here, this is a NumPy array, and you perform operations on matrices and vectors. So here X would be our training data, which is a NumPy array, and W would be our a NumPy array as well. As you can see, I've initialized it over here. So what this function does is that it returns the probability score for given the training data and our weights. And like I said, NumPy is as easy as it looks. Here we are doing the exponential function. Here we are doing the dot. So the NumPy dot actually helps us in the matrix multiplication. And as many of you would have studied high school math, when you multiply two matrices, the column of the first matrix should be equal to the row of the second. So that's why I do a weight dot transpose here. So this will return to me a probability score. Now here I have some dummy weights initialized. Again, you can play with this. I've initialized with some arbitrary values. You can assign any values, but it should be of the size 6, because here we expanded our training sample to have 6 columns. So if you have it 7, then you should have it 7 over here as well. Now, so you can see this returns us a probability score. We got the probability score now. We have the model, we have the probability score. What's the next thing? Next thing is finding out the evaluation. So in the machine learning workflow, I told you about evaluation. So this is where you have a cost function. In this case, we'll be using binary cross entropy minimization. And I hope Shinjini has explained to you about it earlier. So this is the loss for one sample, and this def compute loss function, what it does is that it averages the loss over all the samples. So this is the 1 by L. So in this loss function, x dot shape 0 would be giving us the length of the samples, And in the end, we are returning the loss for loss averaged over all the samples. We have our loss. This the value 0.69. Pay close attention to this value up to 2 decimals because we'll be changing this. We have the loss. Now we need to minimize the loss. This is where the optimization part comes in. So we train our model with gradient descent and compute the gradients for the given weights. Here's the formula we'll be using. So this is the mathematical formula which I presented on my slide, but this is how you calculate when it comes to matrix vector calculus. So someone was asking in the chat, how should I get started with deep learning? Your matrix vector calculus should be to the point. If you're in first year, then pay attention to all the math classes. It'll help you. And this is the formula when it comes to matrix vector calculus for the gradient. Now this compute grad function, again, we get the probability and we calculate the gradient according to this formula. Now, if you would have noticed, I was talking about that matrix thing, that nabla, that ulta triangle thing, that is called nabla of C and the gradient vector. So this is the gradient vector. So this is nothing but for each of the weights, of the 6 weights, it is calculated the gradient with respect to our binary cross entropy loss. Okay, so we have the gradient. Now what to do next? So this is just a function to display the training process. Now we have the training process, which is an iterative process. So when I talked about neural networks, I told that in the analogy, what I said that, yeah. So we send the both teams from the input layer to the output layer, and then they're back to the input layer, then back to the output layer. So the iterative process is called the training process to find the best solution to our problem. And so we'll be training our classifier, which is our logistic regression function, using stochastic gradient descent. I talked about gradient descent, right? So when you apply gradient descent in program, when you program a gradient descent algorithm, what you do is that you calculate the loss and train you calculate the gradient of all the samples at the same time, which is computationally very intensive. And so what the stochastic gradient descent means is that it tries to update models parameters more frequently. That is, the model's parameters are altered after computation of loss on each training sample. So in gradient descent, we were looking at all samples at the same time, but in stochastic gradient descent, we were looking at each training sample, like one training sample per time. So per time unit, as I'd rather say. The next thing is mini batch stochastic gradient descent. In stochastic gradient descent, you have one sample. Mini batch would be, you have a batch of m samples. Why not, why to go for one sample at a time? You could go for m samples at a time. And this is a simple iterative process, training process, where I've taken a batch size. So these parameters, alpha and iter and batch size, will be coming on to later in tomorrow's session. These are very important parameters, and you could change these parameters as well. So I've taken a batch size of 4, and for those 4 samples, I'll update and I'll train for those 4 samples at a time. So I have a for loop for this, and this is the number of iterations, that is 100. So for 100 cycles, it will be going on the process. And this is how our loss is minimized. If you could see, we started up from here, and then we finally reached here. And so this is all about the training process. As you could see, I told you that you need to keep in mind the figures. So previously the loss was 0.69. Now the loss is 0.30. That means we've successfully trained and updated our weights. And here you can have a look at the dummy weights. So we started off with 0, 0, 0, 0. And now we have the final look at the weights. So stochastic gradient descent and mini batch gradient descent are, optimizers, which are available in a framework called TensorFlow, which we'll be coming on to again tomorrow's session. For now, you can have a list of other optimizers which are available. And Adam, I'd like to highlight here, is the most commonly used. So do have a look at this in your free time. And I've listed out, and I've given a really nice Medium article over here, so for you to check out these optimizers. And we'll be going through TensorFlow and Keras tomorrow. So that's it for me, guys. A heads up for tomorrow's session, things we'll be covering tomorrow. We'll be going into the aggressive math behind artificial neural network, and we'll be training our own model, fashion data set, where we'll be classifying, I guess it has 9 samples. 9 samples, our model will be learning those 9 samples using custom neural networks. We'll also be introducing you to TensorFlow framework and Keras framework. I think that's it for our session. One more thing I wanted to tell you guys. So in the end, we've prepared for you a nice quiz. So head over to our Discord server, and over there you'll have the NeuRes channel. Do prepare, do solve the quiz because it's available for a really limited time. I guess somebody will post the link to that here as well. Thank you guys. This was all about the session. Also, if there are any questions left, you could ping the questions tab here and we'll be happy to answer.
Guys, we'll be sharing the link for the quiz in the NeuRes channel of the Outer Circle Discord server. So keep an eye out. We'll be sharing it and it'll be open for only a 5-minute period. So I'll share it right away and we'll open the form at 6:35. All right. So if you could all just give a thumbs up through the emojis, I'll know that. All right, cool, good. So I'll share it right now, but the form will be activated at 6:35. We're also very proud to present our sponsors for NeuRes. Actually, you could just move forward. So we have AWS, Log, Sashido, Give My Certificate, Tascade, Balsamic, Shape.ai, Tesseract Lights, Replit. That's it. So we really like to thank our sponsors because they helped us to bring this together, and we're very grateful to them. I will be activating the link at 6:35 p.m. sharp, and I'll also be turning off the responses at in exactly 5 minutes, so 6:40 p.m. So make sure you guys are fast, and whoever is the most correct as well as the quickest will get the swags. All right, guys, the link is now live. You have only 5 minutes, so be quick. All right, guys. Now it's 6:40, so we've closed the forms. We've got a lot of responses. So we're not going to announce the winners quite as yet. We'll announce it probably later tonight or maybe tomorrow, and they will be announced on Discord, and they will further be contacted through private chat for their swags. So I'd like to wrap up the session now, and I'd like to thank everybody for coming. We really are grateful for you to lend us your time, and I hope that Arsh and Shinjini really covered some great stuff for you today, and could leave you with a better insight. So thank you everybody for coming, and I'll see you guys tomorrow when we're hosting the next part, which is day 2 of the DL primer. So it will also be hosted by Arsh and Shinjini, and see you guys there. All right. Good night, everybody.